Okay, hello. So we're going to look at Suvat today. Okay, now this is of course an acronym, it's not a real word, but it stands for this here, okay? And it is the name of all the different formulae that we can use when we're working with displacement, velocities, acceleration and time, okay? Now, there are 5 of these. They are not too awful to try and remember, but actually some of them can be derived by rearranging the others. Okay, so get them all written down. We're going to look at how to use them in just a moment, okay? And also, just pause while you write this down. Write down also what the letters mean. So S is our displacement. That's how far we've gone from where we started, okay? So in layman's terms, we'd call it the distance, okay? Initial velocity, again, in layman's terms, we'd call it speed. There is a difference between speed and velocity. At this level, in maths at least, don't get too caught up on that. Again, with final velocity, then we've got acceleration and time. And just note here, okay, there's a couple of things I've just written underneath. So meters per second is how we'd normally measure velocity. We could do it in other units, okay? Meters per second is the most common. This actually means the exact same thing. Meters per second to the -1, ms to the -1. It is the same thing, and you will see these used interchangeably, okay? And I don't want you to wonder what on earth's going on if you see them both being used. I think I've actually used both of them. It is kind of a personal preference thing. This does rearrange. If you were going to do laws of indices, okay, you could actually apply them to this, because s to the -1 is the same as 1 over s, and that's still being multiplied by m. So m times 1 over s is the same as m over s, which is m slash s, okay? So they are the same thing. But the final velocity is measured the same way. Acceleration is actually meters per second, okay? So I'll just do a little note down here, but meters per second becomes seconds squared, okay? And the same rearrangement there. So either or, absolutely fine. I just want you to be quite aware of those if you see the opposite one being used to what you're familiar with, okay? They do mean the same thing. So just pause and take note of those. Make them really prominent, because we're going to keep referring back to them. Okay? Right then, we're going to start putting them to use. So here's a kind of a standard type of question you'd get. A car accelerates from 10 meters per second to 30 meters per second in 5 seconds. What is its acceleration? So the first thing you're going to do when we work on these sorts of questions is to write out what you know. Okay, so we're accelerating. We don't actually have an acceleration speed. That's what we're looking for. Okay, so we're going to write down it started at 10 meters per second. Okay, so our u, that's our initial velocity, is 10 meters per second. Okay, that's our, I'll bring this back over, initial velocity. That's what we started at. Okay, so initial speed. V is our final velocity, and that's 30 meters per second in this case. Okay, because we've started at 10 meters per second and it's accelerated up to 30. Okay, so there's your initial and there's your final velocity. And we've also got time, okay, which is 5 seconds. Now that's just something to be aware of, okay, that actually we're working in seconds here. We've got meters per second. If your time is given in something else, minutes for example, you will need to convert it into seconds. That's a really important thing with compound measures. We need to make sure that actually we're working with consistent units, okay? So we've got time, and we're also interested in acceleration. Okay, so we're going to put A there, and that's the 4 pieces of information we've either got or we know. This kind of approach will perhaps take you back to when we did trigonometry, where we were trying to decide which ratio to use. Okay, so we've got U, T, V and A. So we're going to have a look at our list of formulae. Okay, and the one that we're probably going to need here is going to be velocity equals initial velocity plus acceleration times time. Okay, we don't actually know the displacement, neither are we interested in it. We're not asked how far the car's gone, we're not told how far it's gone. Okay, so we're not particularly interested in anything that contains an S. So here's the formula that we're going to need. And once you've kind of settled on that, actually it's quite a nice piece of work. You may have seen this in physics. I'm not sure if you've done it in physics yet. It's a bit of a grey area between maths and physics. It appears in both. So we've got V equals U plus AT, We're going to substitute in the numbers we know, and don't forget when we're substituting in, we don't worry about the units, okay, we'll leave those for now. So we've got V, which is 30, equals U, 10, plus A, we don't know, so leave it as an A, T, okay, 5. So A times 5. I'm just going to rewrite that a little bit more, what we used to, 30 equals 10 plus 5A, okay, just so that's something we're a little more familiar with. And now we're going to solve it for A. Okay, so, I mean, if you really wanted to, you could rearrange the formula to begin with to find out, you know, make A the subject. That's okay if you want to do that, okay? You'd end up with something that looked like this. V minus U over T equals A. Okay, you can do that, but the problem we start to run into is that you're going to end up with a lot more things to remember, and you've already got enough, okay? I would suggest not worrying about doing that, but actually just getting proficient at rearranging and solving, okay, like this. So we're going to subtract the 10, 20 equals 5A, therefore 20 divided by 5 is 4. So A is 4, and now don't just leave it like that, go back and just check. Acceleration is in meters per second squared, okay, or meters per second to the negative 2, it's done there. Make sure you do that to it, okay? We are working in meters per second, so that is the units we're going to use. So it equals 4 meters per second, negative 2. Okay, so there's the acceleration. Right then, we're going to do some more of these. Make sure, I would recommend taking some notes on these, okay? These is kind of like, you know, examples in your books. Okay, this time we've got an aircraft travelling at a speed of 60 meters per second. Actually, note this time I have used M/S. Okay, I have tried to interchange them so you get used to both. When it landed, it took 2 minutes to stop. What was the acceleration? Now, there's an interesting thing here, okay, and I've used it purposely. Acceleration doesn't necessarily mean going faster, okay? It can mean going faster or it can mean going slower, okay? We don't tend to use the word deceleration. It does appear occasionally, but generally speaking we use acceleration to mean any change in speed, okay? So, or any change in velocity. So let's again write out what we know. So we've got a speed of 60 meters per second, so that's our initial velocity, that's what we started at, okay? So that's U is 60 meters per second. When it landed, it took 2 minutes to stop, so that's our time. Okay, and again, like I said before, 2 minutes, we are working in seconds here, okay, so don't write in minutes, we're going to put that as 120 seconds. Now then, there's an extra piece of information hidden in here that you might not spot straight away. Here we are, to stop, okay, its final velocity is 0, okay. That's really important to try and notice those things. You're not always given numbers for the information you're told. Okay, it might be in words. So if we know it's stopped, it's not going anywhere, so its velocity is 0. That's important. And the last thing, we are looking for the acceleration. Okay, so we've got U, T, V and A. Once again, actually, we are going to be using the first one of these. Okay, we're looking for acceleration. So write it out. There we are. So we've got V equals U plus AT. We're going to substitute in what we know. So V is 0, U is 60, plus AT. So I'm going to write it the right way around. First time here, 120A, okay, or TA we could always do. The reason it's written AT is because we always write alphabetical if we can. Right then, so we're going to solve it. Now, watch out, okay, because we are going to end up with a negative, and the reason I know that is because the plane was going slower. If it took 2 minutes to stop, it was slowing down, okay, so we're going to get a negative acceleration, 120A, so therefore we get, well, negative 60 over 120 is a half, negative a half, so we'll put negative 0.5 meters per second squared, okay, is the acceleration. So yeah, if we've got a negative number for our acceleration, it actually means the vehicle, in this case the aircraft, was slowing down, okay, it was not speeding up. So that's always a good way to check, okay, if you know from what they've told you in the question it should be going slower, it's slowing down, then your acceleration should be a negative. Okay, let's have a look at another one. This time I've actually included something which asks about the distance. Okay, so we're going to be looking at some of the different formulae. So there's two parts to this question. Got a vehicle accelerating uniformly along a straight road. Okay, uniformly means its acceleration isn't changing, okay, it's just going to be a consistent acceleration. Along a straight road, increasing its speed from 4 meters per second to 30 meters per second in 13 seconds. First of all, we want to know the acceleration, okay? So we're actually going to be, for the two parts, looking at two different formulae here. So acceleration, let's first of all get our information down. So we've got from 4 meters per second, so that means that's our initial velocity. U equals 4 meters per second. Its final velocity is 30. That's what it went up to. And its time was 13 seconds, and that's already in seconds. And we're looking for the acceleration. Okay, so again, we're going to use that same formula because we're not at this point looking at the distance. Okay, so we're going to use that same formula again. V equals U plus AT. And it's very, very similar to what we've just done, just different numbers this time. Okay, we've got 30 equals 4 plus 13t. 26 equals 13t. Therefore, t, goodness me, sorry folks, A. Okay, therefore A equals 26 divided by 13, which is 2. Okay, and what we're looking at acceleration, okay, so meters per second squared. Okay, now that sounds right, it is going to be going faster, and they actually tell us it's increasing its speed, okay, so it should be a positive number. Now we've got part B. We're going to be looking at the distance this time, so we can actually, it's the same scenario, so all of this information here is still relevant, as is this. Okay, all of this is still absolutely relevant, you don't need to write it all out again. And let's have a look. So we actually are looking for the distance, okay, and we have got quite a lot of information. We could almost have our pick, really. We could use this one. Okay, we've got the information for this. We'd have to do a bit of rearranging though, because the S, which is what we're looking for, is over here. So we might as well use one that's already kind of in the right way for us. Both of these would work. Now the reason that we've got two different ones, they look almost the same, there are a few differences, but sometimes you won't know final velocity or you won't know initial velocity, okay, so in our situation actually we know nearly everything we need, okay, so we really can choose. And the same here, this is quite a nice one, half U plus V multiplied by T. Okay, so let's have a look at that one, that looks quite nice. Okay, again, they will all give you the same answer. So we're going to just write that out here. So S equals a half U plus V multiplied by T. Okay, let's substitute in what we know. And actually, we could have used this. Actually, the nice thing about it, we could have used this had we not done the acceleration question, because it doesn't involve acceleration. Okay, so we get S, we're still looking for, a half 4 plus 30 multiplied by 13, okay, which gives us, well, we could do a few of these in a go here, can't we? So 4 plus 30 is 34, we could times it by the half, which gives us 17, and we get 17 multiplied by 13, okay. I'm just going to grab a calculator and work that one out. There it is. So 17 multiplied by 13, so it's 221. And let's just make sure we've got some context to that, okay? That is the distance, and we've been working in meters and seconds, so that will be in meters, okay? Whatever you put in, whatever units you put in are the same as what comes out, okay? So it's going to have moved 221 meters in that 13 seconds. Right then, let's try another. I think this is the last one of these, and then you're going to be able to try some for yourselves. Let me just check. Yeah, this is the last one. So another two-part question. There's a train moving at a speed of 2 meters per second on a level track, and it reaches a steady incline, which slows it down, or which slowed it down to rest. Okay, so it stopped in 15 seconds, and then actually it caused it to reverse. So basically, a train was going up a hill, it couldn't keep on going, so it stopped and then started to roll back down again. Okay, so first of all we're going to calculate the distance it moved up the incline. Okay, so that's our first step. So get all our information out. What have we got there? It's moving at 2 meters per second, so that's our initial velocity. 2 meters per second. What else have we got here? Steady incline. It's slowed down to rest. Okay, so our final velocity was 0. Okay, it slowed down to rest. That means it's stopped. And our time it took for that to happen is 15 seconds. Okay then. The fact that it reversed at this point isn't really relevant. Okay. In fact, I don't think at any point it's relevant. We'll see. Okay, so we are calculating the distance. Okay, we're looking for the distance, so we're looking for S. Why we use S and not D, I'm not sure actually. It would make life a lot easier, wouldn't it? But there we go. So we've got U, V, T and S. So that's no good, it doesn't have S in it. This one does, but it's got an acceleration and we don't have an acceleration. Okay. Again here acceleration we can't use those, but this one here we can. S equals half U plus V. T, same as what we used before. Okay, that's the one that's going to be helpful to us. So we'll write it out. S equals a half U plus V multiplied by T. Let's plug in what we know. So a half 2 plus 0. It might seem really unnecessary for me to write things like this in. Clearly 2 plus 0 is 2, but actually, as I'm always asking you to write your working out, this is exactly what I mean. Okay, it's really easy to make a mistake and write the wrong number somewhere. Okay, if you show in each step of your working, if you get to the end and your answer doesn't seem sensible, you can go back and each step you can just check what's happened. Okay, right then, so we're going to get a half multiplied by 2, so 2 divided by 2 essentially, which is 1 times 15. Okay, which is 15. What are we working out there? The distance. Okay, so it's actually moved 15 meters up this incline. Okay, so actually went a meter per second. Yes, that's right. I thought I'd read something wrong, then I thought that was telling us the acceleration. Yeah, okay, so nice. So it's gone 15 meters in 15 seconds actually, so it's actually gone a meter a second, which we can really just answer that now. However, let's just make sure we prove it, because if we work this out and we don't get a meter per second, then something's gone wrong. Okay, and we can figure out what's happened. So the acceleration, so let's just maybe highlight or just kind of stand out the bits of information that we've got so far. And we've also got equals S, there we are. So we've got S, V, U, and we're looking for acceleration. Oh, and we've got time as well. There we are. So there's a few different ones. This is the easiest one. We've got the information that we need here. We could use the distance as well, although actually it's not necessary to use it. So again, I'd go with the one that's got the least work. Okay, don't make it complicated for yourselves. So V equals U plus AT. Put in what we've got. Let me see this. 0 equals 2 plus acceleration, of course that's what we're working out, times 15. Okay, and we are going to subtract the 2, so we get negative 2 plus 15a. We're decelerating, aren't we? It's going to go slower. So yeah, that's right. I thought I'd gone wrong then. That's actually going to give us negative 2 divided by 15, which is not going to be a very pleasant number. I'm just going to bring that up over here somewhere. Okay, so negative 2 over 15 equals A. Okay, well that doesn't seem right, does it? If we went 15 meters, of course it's acceleration. Of course it wouldn't. Okay, even I've done it there. I've actually mixed up my velocity and my acceleration. Okay, so yeah, negative 2 over 15. Okay, we get 0.13 recurring. So 0.13 equals meters per second squared. Okay, and actually that's our acceleration or deceleration, so it's a negative. deceleration. So yeah, let me just clarify what my mistake was there. Okay, I was thinking, because I think it caught my eye because we had 15 here and 15 here, and as you guys know, when we're doing our maths, we're always looking for patterns. Okay, and as soon as I saw it, I was like, brilliant, there's a pattern here. 15 meters in 15 seconds. Then of course they were going at 15 meters meter per second. Okay, that makes sense. But that's not an acceleration, that's a velocity. Okay, that's a totally different thing. So always worth double checking. It's a good job we did, really, isn't it? It's a really good job that I checked that there, because had I leapt in and just said, well, it's just that, I would have been wrong. Okay then, so there are some examples for you to try. A really big mistake at the end by me, which should hopefully help you avoid that mistake yourselves. Okay, let me know how you get on.